Or thank you.
I don't know what is happening when I share. It goes to where I cannot see it. Let me again share. Okay. Now, so welcome back. We were looking at elliptic curves, and so far we've looked at a lot on elliptic curves. We looked at Montgomery curves last time, and we said that these Montgomery curves are a type of elliptic curves that are commonly used in real life situations. The Montgomery curve. So we were to also look at the twisted Edwards curves, which are also used in the real world. But I thought somebody had asked to look at bilinear pairing, and then we'll go back and look at those twisted Edwards curves because they're very much common in real life situation applications. Now, bilinear pairing is also a very good a very good tool that is used in cryptography, especially if you want to look at securing data, that is encryption and decryption. And if you want to look at, let's talk of maybe something post-quantum. You want to see that, you want to ensure that your data is quantum secure, post-quantum secure. And bilinear pairing is part of what then you'll be looking at. There are several other things we'll be looking at to ensure quantum post-quantum security. But bilinear, when if you're doing on elliptic curves, when you are doing on elliptic curves, then pairing is one way that you can achieve post-quantum security. Pairing is one of the ways. If you are, elliptic curves, most of the crypto systems that are done on elliptic curves are not secure, but those that are done on pairing, where bilinear pairing is one of them, are thought of as being a post-quantum secure. We have other ways of ensuring post-quantum security, and we'll be looking at those other ways later. But for now, we're still looking at elliptic curves. So I've said that bilinear pairing is on elliptic curves are tools that are used in cryptography to construct protocols such as identity-based encryption, attribute-based encryption, and short signatures. Now, in bilinear pairing, what are we talking about? We're talking about two elliptic curves, not necessarily two elliptic, but two groups. We're talking about two groups and another group. So these two groups could come from two elliptic curves. So if you have, let me talk of elliptic curve. Let's talk of elliptic curve 1, elliptic curve 2, and maybe another elliptic curve. And what we know is that elements points of this elliptic curve would form a group. Points of this one would also form a group, and the points of this one will form another group. So we have three groups here. Points of each elliptic curve together with the identity element forms a group. And the points of another elliptic curve together with the identity element forms another group. So we have three groups in this case. So therefore, what is bilinear pairing? Bilinear pairing, therefore, is just a map. It's a map, this map E, and this map E, or a function, you can say a map or a function, and it's mapping these elements, these points, to these points. So this is a group from one elliptic curve. This is another group from another elliptic curve, and this is another group of another elliptic curve. So the points, the function that maps these points, the points here to these points, is what we call bilinear pairing. I just want again to remind you, we had three elliptic curves. And another elliptic curve. And this elliptic curve had points. And apart from those points, also has the identity element. So the points of this elliptic curve, together with the identity element, which we call the point at infinity, they form a group. And the elements of the points of this and the elliptic curve, together with the point at infinity, will also form another group. And we have another one again. The points of this elliptic curve, together with the point at infinity, will form another group. And now, the map or the function that maps the direct product of the group 1 and group 2 to group T is what we call bilinear pairing. Now, there's one thing you must, of course, for it to be a bilinear pairing, it must fulfill some conditions, not just that it becomes a bilinear pairing automatically. It has to fulfill some conditions, and we shall be looking at those conditions. But again, just remember that this group and this group will be additive groups, and this is supposed to be a multiplicative group. So this group and this are additive, but this one should be multiplicative, so that now the product of this is mapped to that. So this will then be a multiplicative group. This will be a multiplicative group, but these are supposed to be additive groups in bilinear pairing. So for this function that is mapping the direct products of these two groups, additive groups, to this multiplicative group, for this function to be a bilinear pairing, it must fulfill these three conditions. The first condition that it must fulfill is bilinearity. And what do we mean by this bilinearity? You pick a point from group 1 and a point from group 2, and then pick scalars. These are just numbers, could be 1, 2, 3, 4, from the integers. Now, if you take this first integer and multiply the point from the first group, and this other integer multiply this from this other group, this map would map this thing to this. So what has just happened is that this integers just comes and becomes a power. So we have the power. So that is AB and so on. So this becomes that. Now, so if you read some books, you'll find it expressed a bit differently, but they mean the same thing. Because if you read some books, you find it expressed this way, that E maps P raised to A, no, R raised to that as E P R A B. So it means the same thing. It means the same thing. You see, what does this mean? This means P plus P plus P A times. It means you're adding P to itself 8 times. That's what it means, AP. And it's the same thing that we have here. Just the same thing. Of course, you're doing it mod something. And you see, this is an additive group. This is an additive group. So an additive group, 2 times 3, where 2 is an integer. And let me say that this is a mod. Okay, this is 3. Let me say I'm doing it mod 5. Just an example, just to show you that these are equal, are the same. So if I say 2 times 3, this is just 6, which is 1. And it's the same as 3 plus 3. So you're doing it those number of times. You're adding it 2 times. Now, but now for an additive group, if someone writes it a power like this, it doesn't really make a lot of, it does not necessarily mean that I'm multiplying P 8 times. It doesn't mean that I'm multiplying. In this case, if I wrote it like that, it doesn't mean 3 times 3, because it's an additive group. And an additive group, we do not have multiplication. Actually, we are not multiplying. It just means 2 times. This 2 comes, and it's like that, 2 times 3. In fact, the best way of writing it, since it's an additive group, is this. Since it's an additive group, this is the best way of writing it. But when you read books, you find them expressed sometimes this way, which is not very much okay, because we are talking about an additive group. But once you realize that you're talking about an additive group, then you must know how to interpret it, that it means that you're just adding P to itself 8 times. You're adding P to itself 8 times. Once you realize that you're working with an additive group. Of course, the groups on the left side are additive groups. Now, so that is the first property, that this map must satisfy to be bilinear pairing. The other property is non-degeneracy. Non-degeneracy. And what non-degeneracy means is that the pairing, the map does not map everything to the identity element in this. So the elements will not be mapped. It will not map everything to the identity element. For instance, what that means, that if the point P is not the identity, and if the point R is not the identity, then this map would not map this to the identity 1, do not map it to 1. When this, you see, for a multiplicative group, For multiplicative group, the identity is 1. So where this element, this point and this point are not identity elements, then the map will not map to the identity. It will not map the identity. So that is what we mean non-degeneracy. So it will only map elements of the identity if the points in question are identity element, are also the identity points, are points at the infinity, for instance, in this case. That's what it means by non-degeneracy. So it will not map anything to identity if what the points on the left are themselves not identity elements. Then the last property that it must fulfill is computability property. And what this means is that if it has to be bilinear pairing, then there must exist an algorithm that can compute this. There must exist an algorithm that will compute it. But if no algorithm can compute this, then it's not a bilinear pairing. It's not. But for it to be, there must be an algorithm that can compute it. So that is the last property that it must fulfill. Now, just before we go into the details of bilinear pairing, I thought we should know some terminologies. And the first terminology that I wanted us to know is that if the first group and the second group are equal, then this pairing shall be called symmetric, shall be called symmetric pairing. And and in that case, or in any of the cases, where we are mapping G1 cross, okay. So it's G1 cross G2 to GT. In any of these cases, the groups on the left side, we refer to them as pairing groups. The groups on the left side, G1 and G2, are referred to as pairing groups, or we can also refer to them as source groups. But then the group that we are mapping to is what we refer to as target group. So some books will be referring to them as target groups and so on. So that is a group. So when we use the word target group, and then you know that is a group we are mapping to. And when you hear us refer to groups as source groups or pairing groups, then we are referring to groups on the left side of this equation. Now, so I thought also it's good to recall what we have done so far, so that we then use it in bilinear pairing. One thing that we've done so far is we've known the equation for the elliptic curve, the short waist arrays, and we know the condition for this equation to be elliptic, this non-singularity equation. Now, the other thing that we also know is that if you are given an elliptic curve E of a field F mod Q, so this is elliptic curve of a field F mod Q, together with the point at infinity. I should have written it that way, just to be consistent with my symbols. I should have written it that way. Now, together with this, so the points of this elliptic curve, together with the point at infinite, form an abelian group. And this we've already said. And addition, they form an abelian group. Now, so the groups on the left side, G1 and G2, will come from this same group, from this same elliptic curve. They should be subgroups. There should be subgroups of this elliptic curve. So this elliptic curve has several groups, has several points, This elliptic curve has several points. And so you're saying that the first group would be a subgroup of this, could be maybe that, and maybe the other one is that. So you're saying that it's a subgroup of the entire group. And you're saying that they are additive groups. And this should be a multiplicative group. So this one is also coming from this, but after removing zero. So it could come from this, or it could even come from an extension of this, but without a zero. So you remove a zero. We talked about extensions last time. So you can have that, or you can have that, and so on, where the power there is the degree of the non-reducible polynomial that I used to form this extension. We talked about extensions the other time. Now, so what is important is that the first two groups are emanating from the elliptic curve E mod over a field F mod Q, and the multiplicative group that we're mapping to is emanating also from E, at this time over F mod Q, and this F is a multiplicative group. You've eliminated the zero from it, and it could be it could be mod Q or mod Q raised to K. Now I'm interested with K. So I'm interested with F K. This K can be 1, can be 2, can be 3. So if K is 1, then we just come back here, but now without a zero. If K can be 2, K can be 3, and this K is what we call the embedding degree. This K is what we call the embedding degree, and today I just want to teach you how to get the embedding degree, because we'll be using it then in bilinear pairing. So you need to know what an embedding degree is, and then how do you find it? That is what is very important. And today, of course, we'll look at a code that will be giving us this embedding degree. So that is once we are done with the embedding degree, then we end our lesson there today. So then now I define the embedding degree, and I've shown you how we've come up with it. Let me just go back and show you where it's coming from. We began with bilinear pairing, and we said is the map that maps group 1 by group 2 to group T. And these groups are coming from one, let's just now stick to one elliptic curve. Let's say they're coming from this elliptic curve. And this elliptic curve is from the field, let's talk of maybe it's coming from Z. This is a field. Let me remove this first of all. Z5. We talk of Z5. So coming from Z5, so they're mod 5. So you can use Z or you can use F, there's no problem. Once you understand what we mean by a field, there's no problem. You can use Z or you can use F. Now, so G1 comes from this E mod 5, and E2 is another subgroup coming from the same E mod 5. And then, what about this? This is a multiplicative group. It be coming from Z star 5. Now, this star 5 could be raised to K, where K could be 1, 2, 3, and where K, therefore, is just the degree of the polynomial that is used for this field extension. For the field extension. So K could be 1, could be 2. So if K is 1, then we just talking about Z5 star. If K is 2, we are talking about Z5 raised to 2 star, and so on. So this K is therefore what we call the embedding degree. And what is important to us today is how do we calculate K? How do we find K? That is what is important to us, so that we'll see how to do it manually, how to find K manually, and then see how to find K using Rust code. So then I define embedding degree. We've seen what it is, but now what is the definition? The definition is that the embedding degree K is the smallest integer R is the smallest integer such that R divides is the smallest K. The K is the smallest integer such that R divides Q. Remember what Q was. Q is coming from our field, the mod. So Q raised to K minus 1. R must divide this. So if R divides this, the smallest integer that makes R to divide this, the smallest integer K that makes R to divide this is what we call the embedding degree. But what is R? R is the order of group 1. R is the order of group 1. I mean, R is the number of elements, the number of points of group 1, the number of points of group 1. How many points does it have? That is the order. Now, that smallest integer that allows R to divide what is on the right-hand side is what we call the embedding degree. So let's look at the following example. We are given this elliptic curve, this, and once you are given that, you must know what the elliptic curve is. So I talked about this last time. So if you are given this, you understand that the first letter here stands for A, and the second letter stands for B. So that means this elliptic curve is the same as y squared is x cubed plus ax, but a is 1, plus b is also 1. So this is the elliptic curve. Now, but the question is, consider this elliptic curve and it's defined on F5. What is the embedding degree? Find the embedding degree for this elliptic curve. Now, let me again remind you before we do it. Before we do it, we say embedding degree is K that allows R to divide Q raised to K It seems my network is unstable. Okay, let me just repeat what I had already explained about this question. This question, we are asked to find the embedding degree. We've been given the elliptic curve, and we've been told the field over which this elliptic curve is defined. What is embedding degree? Embedding degree is the K that will allow R to divide Q raised to K minus 1. The smallest of them, because there could be several Ks that will allow R to divide this, whatever is on the right side. But they're not all of them that we call the embedding degree. The embedding degree is the smallest of them all. The smallest of them all. There could be several Ks that will allow R to divide, but they can never be all of them the embedding degree. The embedding degree is the smallest of them all. Now, what is R in our case? In our case, is the order, R is the order of the elliptic curve given to us. And what is Q in this case is 5. So then we're asking ourselves, first of all, what is R? Let me just share my code. My code that I'll use it to find the order of this elliptic curve. We have the code for finding the order of elliptic curves. So what I only require here is a mod, which is 5, A, which is 1, and B, which is 1. So then I share my code to find the number of points on that elliptic curve. The number of points on this elliptic curve, I need A. A is 1, B is 1, and our prime is 5. So then, how many points does this elliptic curve have? Now, this code, we had it earlier when we were looking at when we are beginning elliptic curves. We saw this code. Okay, and then it tells me that the elliptic curve is of order 9, has 9 points. Elliptic curve has 9 points. So that means that in our case, R is, in our case, R is 9. And Q, we say, is 5. Can you hear me? I can't see, okay. I thought my internet had gone off, but I can see I'm still on. I thought I had disconnected. So Q is 5. Okay, so Q is 5. R is 9. What else do we require? We require K. So K is what you're looking for. K is what you're looking for. And is the smallest of all the numbers that will allow R to divide Q raised to K. So we then use trial to find out which of the numbers. So we are doing it mod 5. We are doing it mod 5. So we are trying all numbers mod 5. Trying 1, 2, 3. So R is 9. Can it divide 5 raised to 1 minus 1? You see, this is the same as 9. Can 9 divide 5 raised to 1 is just 5, so 4. 9 cannot divide 4. So that means, this means that 1 is not the embedding degree. It's not the embedding degree. Let's try to. Now, this is the same as, can 9 divide, this is 25, 24. You can see that is not possible. So again, 2 is not embedding. So we are saying that K will be the smallest number that will allow K to divide whatever is on the right side. 1 has failed, 2 has failed. Let's try 3. Okay, so you're asking yourself, 5 raised to 3, then minus 1, can 9 divide that? So this one I can use my calculator. I can use my calculator here. 5 raised to 3 is 125. So when I subtract 1, 124. Can 9 divide that? 9 cannot. 9 cannot divide that. Then let me try 4. Of course, you are trying mod 5. Mod 5, the numbers, you are trying 1, 2, 3, all the way to 4. 4 is the last one. Then minus 1, let me see. 5 raised to 4 is 625. Then subtract 1 from it, you have 624. Can 9 divide that? 9 cannot divide that. Is my calculator, am I doing it correctly? Anybody that has a calculator and is following? Uh, 9 raised to 4. Oh, what is it? No, it's not 9 raised to 4. It's 5 raised to 4. Okay, let me again try it. But first of all, we need to know the definitions of R and what R. I've said R is the order of the subgroup. And what about Q? Q is the mode. Q is the mode. So it should give us the results. I done it here. Oh, just a minute. There's something I left out. Once you find the order, of the group, you're supposed to find the prime numbers. of that order. That is what I had left out. Something I had left out. Once you find the order of the group, you must find out how many prime numbers divide that that order. So in this case, we only have one prime number, which is 3, and 3 divides that. So once you've known what prime numbers are there, now those prime numbers are the ones you'll be using as your R. Are the ones you'll be using as R, not necessarily the order. Not necessarily the order, but the prime numbers that divide that order. So that is why I've said the embedding degree K with respect to the factor 3. 3 is the factor of 9. Should be the smallest integer such that 3 divides this equation. The smallest integer such that 3 divides this equation. So we not necessarily the order of the group, but the prime numbers that divide the order of the group. So those are our R. That is our R, the prime numbers. So that is what I need to, I think I need to change here. I need to change here so that this one, R becomes the prime numbers that divide the order of the group. The prime numbers that divide the order of the group. So that is what I need to change there. Now, so the prime numbers dividing, the order here is 9. So the prime numbers dividing 9 are 3. And so we are checking the smallest integer that makes 3 divide the equation on the right side. So you try 1, 5 raised to 1, then minus 1 before, 3 cannot divide 4. 3 cannot divide 4, so 1 is not the embedding degree. Now try 2. 5 raised to 2 would be 25, minus this would be 24. And you can see 3 can divide 24. 3 can divide 24. So that means this number is the smallest one that has made 3 to divide this equation. Therefore, the embedding degree for this elliptic curve will be 2. That will be the embedding degree for that elliptic curve. To be 2. Now, so let's just repeat so that you know what we require for the code to give us the embedding degree. For this code to give us the embedding degree, first of all, we already have the elliptic curve, so we just give it A and P, A and B, and then P. Okay. So what we then want are the points, how many? And then the factors, how many factors are there? So that means if it has 2 factors, for instance, a number like, supposing the order was 6, the prime factors of 6 are 23. So it means this elliptic curve would have 2 embedding degrees. Would have 2 embedding degrees. One embedding degree with respect to this, another with respect to this. So it will have 2 embedding degrees. And what about a number like 27? 27 has 3 only. So it will have 1 embedding degree. 3 is the only prime factor. So the number of embedding degrees will be equivalent to the number of prime factors the order has. The number of prime factors the order has. Now, so we are now writing the code. If you're writing the code, what we require is the prime factors. For me, what I did, I did not give it A and B. The one I have is the one that I already have. I already have the prime factor. I use a different code to give me the order. And then using my own ways, I get the factors. Using a different code, I get the factors. And once I have the factors, now I do the one for the embedding degree. The embedding degree, I'm just giving it one of the factors. And I also give it my prime number, the mod. I give it the mod. So once I give it the mod, and I give it one of the prime factors, it should be able to give me the embedding degree. So I'll only be giving it the mod and one of the factors of the order of the group. That means I must have a way of getting the order of the group. Now let's find the order of this group so that we proceed. And this is 8.8 mod 13. Looking at this example, we need to get the embedding degree. So A is 8, B is 8, and F mod is 13. So let's find out how many elements does it have. So A is 8, B is 8, and our prime number is 13. And how many elements does it have? This one has 20 elements, 20 points. It has 20 points. So then I need to find out what are the factors of 20. How many factors do we have? That's what we need to find out. But we've already found out the order of the group. So the group has 20 points. So 22 goes here, 10 times, 2 goes here, 5, and then 5 goes there 1. So it has 2 prime numbers, 25. So we expect 2 embedding degrees. One corresponding to 2, another one corresponding to 5. Of course, those are the prime factors of 20. So that's what I've said. The group has 20 elements, and the 20 has 2 factors, 2 and 5. And therefore, we need to get the embedding degree for this and the embedding degree for this. So I began by calculating the embedding degree for factor 5. So it is, what is embedding degree for factor 5? We are looking for K that will make 5 to divide this. K that will make 5 to divide this. Now, so I'll try K from 1 to 12 because we are doing it mod 13. When K is 1, I have 13 minus 1, which is 12. And 5 cannot divide 12. So there is supposed to be a comma here. 12 is not divisible by 5. And therefore, 1 is not an embedding degree. So now I try 2. 13 raised to 2 is 169 minus that 168. But 168 cannot be divided by 5. And therefore, this 2 is not an embedding degree. Try 3. 13 raised to 3 will be 2197, then minus 1 will be 2196. But this 2196 is not divisible by 5. So I try the next number, 4. I try 4. 13 raised to 4 will be this. Then you subtract 1, you have that. But this number is not divisible by 5. No, it's divisible. This one you can see the last digit is 0. So this is divisible by 5. So because of that, it means the 4 is the embedding degree when the prime factor is 5. Thus, the embedding degree for this elliptic curve, the first embedding degree is 4. Since we have 2 prime numbers, we must have 2 embedding degrees. But the first one is 4. Okay? Now, what about when the factor is 2? We want to look for k that will make this divisible by 2. That will make this divisible by 2. So we try 1. When k is 1, you have 13 raised to 1, which is 12. Now, when you subtract 1, you get 12. But this 12 is already divisible by 2. So that means 1 is the embedding degree in this case. 1 is the embedding degree in this case. So you can see we've been able to find 2 embedding degrees for this elliptic curve. This elliptic curve had 20 points, and 20 had 2 prime factors. And therefore, each of the prime factors had to give us an embedding degree. Now, but in the future, we'll now be seeing how this embedding degree will be very useful, because we'll be using this bilinear pairing in signatures and also in encryption and decryption. We're looking at discrete log problem in elliptic curves, and we'll be seeing how this is very relevant. Now, so I just want us now to look at the code that will give us the embedding degree. I've already told you what my code is like, but of course you can always customize a few things to the code that it does what you want. But for me, what the code I have, a curve, I'll use a different code to give me the order. Then I'll use a different one to give me the prime factors of that order, or I can even do it manually. Once I have that, the prime factors, and I have the mod, I now come to this code. So this code, I'm only giving it the prime factor and the mod. And so the type of customization that I said, you can now customize this one so that you just give it the elliptic curve and let it give you the embedding factor. If there are 2, let it give to you 2 embedding factors. If there are 3, let it give to you 3. So that one you have to customize. You customize later and see how to do it. But now, for me, what I've done is this. I've already found my R, the prime factor, and my P. And I want K to be mutable. So you see, I'm doing it just the same way we've been doing. We are changing K. So we already have R. Let me say it's 2. And I have my P. Let me say it's 7. I want to begin by letting k be 1. Letting k be 1, then minus 1. So I check whether 2 can divide this. So this code is just checking each of these numbers the way we've been checking. The way we've been checking, so it checks whether 2 can divide this. If 2 cannot divide that, it tries, it changes k. So k now changes to 2. So 7 raised to 2 minus 1. If 2 cannot divide that, it changes this to 3, and so on until it finds a number that 2 can cause to divide this. So this is what we said. Let k be initialized at 1. And then you just enter the loop. And then in the loop, you're now trying each of the values. You're trying each of the values. So you'll be changing the powers. You can see you're incrementing k by 1. Every time it fails to divide, 2 fails to divide, you increment k by 1. That is what is happening. So it will then be let p, the power will just be power raised to p raised to the power, p raised to k in this case, because we began by k. So it's p raised to k, this case. Then let the candidate, we are now focusing on then what will be the answer, or what is the power? The power. The candidate is our power. So the candidate will be the power minus 1. So you see this, what I call the power is this. What is the power? The power is this. Power is p raised to k. That's what I call the power. So when I talk of power, I mean k raised to p. So the candidate will be the power, which is k raised to p minus big integer 1. Now, if this candidate, now this is the candidate. This is the candidate. If this candidate divided by r, if this candidate, and this is our candidate, divided by r gives you a remainder of 0, then you've just found the k you are looking for. If this candidate divided by r gives you a remainder of 0, in other words, r divides the candidate and the remainder is 0, then it means k here is what we are looking for, is our embedding power. So you then exit the loop. You would exit the loop. But now these trials continue. You can continue until you get the k. Now, if you reach a number greater than 100,000 and you've not obtained the k, then it means there's an error, or there's no embedding degree. There's no embedding degree. If you reach a number greater than 100,000, because when you try even when you try bigger numbers like the prime used for Bitcoin is very huge. It's very huge. You'll find its embedding factor is just around 70. Its embedding degree is around 70. So you cannot have embedding degree that is above, irrespective of the number you're using. However big the number you're using is, you cannot have an embedding degree beyond 100,000. So if you find that you've tried up to 100,000 and beyond, and you've not found a value, then it means, of course, that value has no embedding degree, and therefore you just leave it. There's no embedding degree for that one. So this code will try, if it reaches 100,000 and it has not obtained an embedding degree, it will write no embedding degree. Now, what is the main function doing? The function, this code has only two functions. Also, you remember I was doing the other work I'm doing using another code, and then I just bring here the prime factor and the prime number. So there are only two functions here. The first function that we're looking at is a function to compute the embedding degree, and it just computes the way we've explained. And then we have the main function. The main function is just initializing your P and your R, that prime factor. And then after that, it has to call on compute embedding degree, calls on the function just above. The function just above. It calls upon it to match, calculate and then match for this R and P. Then it prints if the embedding degree is found. It also prints if it's not found, if the embedding degree is not found. Now, I just want to use it to do an example that we've already looked at. That example, we had 13 as P, and we had R as 2 at one point, and R as 5 at another point. So P, yes, and 5. Yeah, this, you see, the example I'm looking at is the one that we had the order of the group was 20, and therefore the prime factors were 25. And we said in that case, we find embedding degree when the prime factor is 5, and then find when the prime factor is 2. So I begin with when it's 5, and we find it to be 4. That is the same thing we found. What about when it's 2? When it's 2, what would be the embedding factor? It found 1. Did we find 1? Yeah, it says it's 1. Embedding degree is 1. Now, so as I said, you can modify this code. You can modify it so that it calculates the order. Then after calculating the order, finds the prime factors. Then it does for every prime factor. Embedding degree for every prime factor. You can do that. It's possible you can modify and come up with a code that can do all that, so that you're not doing the rest of the work elsewhere and then transferring here just the prime factor and the P, the mod. So you can customize it to do all the rest, all the work for you at once. Now, a very important point that I mentioned about the elliptic curve that is used in Bitcoin, I already said that although it has a very huge prime, its embedding degree is just about 70. So you cannot have embedding degree going very huge, around 100,000 and above. Now, I had already explained how the code works, and of course, I've also included it here, that at your own time you can look at it As you look on the code, you can come back and see how does this function work? What is the role of this function? And of course, that is how you get to learn how to write the code. Once you must understand what you are typing means and what it does. Okay, that is where I think we should stop today, and then we meet on Tuesday at the same time from Tuesday. Thank you.
Okay, Mwalimu, thank you for the lesson. I think we can meet next Tuesday. Have a nice weekend.